we can actually do a little modeling trick here, a modeling extension that could help us dealing with potential nonlinearities, and also as a way to more formally investigate whether the assumption of linearity is okay or not. So now I'm actually going to do some statistical modeling and statistical testing to sort of support, not only by visual, but actually by modeling. Because it's quite easy to extend our multiple linear regression context and setting into what we could then call polynomial linear regression. Because we could just do a multiple linear regression where I, as the second variable, plug in the squared x, very straightforwardly, done. And then I check in the output, is the squared term important or not? Is it significant or not? If it's significant, I need it. If not, I don't need it, right? So I go check whether I need it or not. That's a modeling way to actually extend the whole business of being on top of it. And let me just show you. It's very small, I know, but sometimes that's how we go. It's very low practical. As I said on the slide, I just define the squared wind. I call it wind SQ, and it's just the square of the wind numbers. I could also do the squared temperature, and I could do the squared radiation. And then I go check whether it's important or not. And if it's important, I put it into the model and I keep it. Now I'm actually doing slightly something that I told you, otherwise we didn't do. I'm doing forward model building, actually, as part of the extension of the basic model. So it's just to say we are, in fact, always finding ourselves doing a kind of a mix of backwards and forwards. That's how real-life modeling, machine learning, you name it, is actually working. Let's try it in R. Not that one until the second. Let's see how it goes. Now my nonlinear patterns here. Now I'm going to check whether it's really something important or it's just random fluctuations. That's what I'll find out now. Let's begin with the wind and just as an example see what happens. So look at what I did. If I just show you in 2 lines. I define a new variable, which is the square of the wind numbers. I add that square. It's not important where I add it in, actually, but here it is. I put it into the model, and I check what the results are. Here are the results. Let me go look at the new one. Is the wind structure I saw in my validation plotting over here, was that important? Yes, it is. Clearly significant effect of the square of wind, so I couldn't assume a linearity. I would need the squared wind in my model to have an adequate description of what's going on. I could do the same. Let's not do all of it, but as you can see now, modeling is a bit of an art, right? It's like we can go up and down, backwards, forwards, checking different things, finding a proper model. In a way, there is no limit to how far you can take this. Now it's square. What about cubic terms or combined terms, x1 times x2? Yes, that could potentially be relevant to think about. What about temperature? Well, yeah, not so clear, but still an indication. I'm looking at the p-value, right? Smaller than 5%, but not extremely small here. Yes. That's checking for nonlinearity or curvilinearity. Question? Question, does the number of stars tell something about the p-value? Yes, is the answer. R has the inbuilt codes that matches our table of evidence of p-values that you were given in chapter 3, actually. It's exactly the same definition of 3-star, meaning what were the words back then? Really strong evidence. Now, I don't remember the exact words from the table. You go check the table. Starting with 1 star, 5% some evidence, 2 stars strong evidence, and 3 stars really strong evidence, with the same levels of 5%, 1%, and 1 per mil. It's matching the table. This is some kind of a global coding of p-values that you'll find in many different softwares like this. So good question and good point too. If you didn't realize it by now, it's good to actually realize it now. So good. Let's see. You ready? 5 out of 8. Come on, there we are. Well, many of you seem to have looked at the wrong p-value, it appears. I'm asking about linearity assumption for the radiation effect. Slightly trick question, but then again, I didn't include any square of the radiation. I only included the square of the wind effect, which was not related to my question. And maybe that was not so much the point, but more the point to say that you couldn't answer the question of whether the linear model is correct by just looking at the results from the linear model, right? That's a misconception that many people actually take. So I'm asking about linearity assumption for radiation here. No, that's an assumption in this model. I cannot check that assumption just by looking at the consequence of that assumption, right? I would have to go look at residual effects, residual plots, or I would have to add the square of the radiation to the model. And the square of the radiation is not part of this output that I showed you, right? So the point being, the output of a linear regression cannot prove whether the linear regression is a good model. Only further investigation can support that assumption. Residual plotting or nonlinear modeling on top of the linear model. One of the large misconceptions of the world also happening in the Danish high school, which we are really trying to change. Anyway. Mellow Mike is in the business. Good job.